let's simplify some code. In here, we will be traversing binary tree vertically by column by column. So let's take a look at this example. And in this example, if we divide this by column vertically, then 9 will be in its own column, 3, 15 will be in its own column together, 20 will be its own column, 7 will be in its own column. So we need to return this in our list of lists. And so how are we going to approach this problem? So if we need to find a way to differentiate them by columns and collect them, all those nodes under the same column. So how are we going to differentiate by columns? So let's say it's like if we assign 0 number to 3, and then if we have a rule saying that whatever is on the left side, just subtract 1. Whatever is on the right side, just add 1. So let's do that. So this is 0. Subtracting 1 becomes -1. This one, adding 1 becomes 1. Now we're here. Let's say we are at 20. And at 20, we're subtracting 1 from it. And then this becomes 0. Now 3 and the 15 are under column number 0. So that's how we can differentiate them. For that, we will need to collect them under a dictionary hash map where it will have a column number as its key and value as a list of all those nodes. So let's jump into coding. So this is our goal to return it. This is our result. So let's take care of when root becomes null, then we'll just return result. And let's define our hash map where we say that the key is our column number, and values will be a list of all nodes values. So this is our map where we collect everything in there. Now we need to define our queue, because like this, we will be traversing it level by level, and this is a BFS style of problem. We need to define a queue, and our queue will hold an information of the given node and its corresponding column number. So for that, we can use map entry, and like I was saying, it will have a tree node and its corresponding column number. Now we can just add root and then assign 0 to its root. So let's make a new entry. We will assign root, and we'll just say for the column number 0. Now we will just need to iterate. So when queue is not empty, so queue is not empty. Now when we are removing from our queue, we'll have a queue entry value, and so we're removing it from first because it's a FIFO, first in, first out. And from here we can retrieve information where we have an access to our current node and its corresponding column number. So we can say tree node. This is our node that we see. Getting a key, because that is a key, and integer, which is a column. This is a column that we are on, and that is going to be q entries get value. Let's do the column number. So in here, what we are seeing, and then it's like, since we have this information, we can add this information to our map, because later from our map we will be able to get a list of all these nodes and add it to our result. So let's do that. So we'll put, we have our column number in here, and we will need to add the list. So first time when we are seeing it, we need to create a list and add to that. And second time when we're seeing it, we will just need to retrieve that list and append new values into it. And what we can do is, so let's get our map list. So map, we can actually do get or default. So we'll try to get column n, and if it doesn't exist, then we will return array list, new array list. So now we have a new array list if it doesn't exist, or if it exists, then it will return us the existing list. So whatever the case, we'll just need to add a new value, nodes value. Now we have our complete map list, and we'll just add it to our map. Now we need to add all other nodes to our queue. So if queue nodes left is not equal to null, we will add last to our queue. So we need to make a new entry, because new map entry, abstract map, simple entry. And for this one, what was the first of the tree node? So we will add our node left, and like we were saying in the beginning, whatever comes from the left side, let's just subtract the parent's column number. Whatever comes for the right side, let's add parent's column number. So we have parent's column number, we'll just subtract 1, and for the right side, we'll just add 1. So let's do the right side. So if not equals to null, q last new subtract map simple entry. Then we are adding the right side of it, and we are adding 1 to our parents. Okay. Now, once this while loop finishes, completes, we will have our map with all those with corresponding with all these lists with the key being column number, and we will just need to add it to our final list of lists. So this, if you've noticed, like this is getting returned column by column. So 9 is getting returned first, then this column, then this column, then this column. So in order to do that, we need to, because like key is in our map, key is a column number, so we need to find the starting column number and ending column number. So for that, we can add some new. So the starting will be minimum column number. Let's just define them, and the ending will be maximum column number. So, and first time when we're seeing column number is here when we're getting it from our queue, removing it, and this is the parent's column number. So every time when it is iterating, we'll try to keep track of the minimum, which will be our start. Column with the column number. And same goes for maximum. So just need to get the maximum one. Now let's just iterate over our column numbers. So starting column number will be minimum column number until it runs until maximum column number, adding 1, and we're adding 1 because like we want to also include the maximum column number here. Now to our result, we'll just need to add map get, and then key is our I. So in this example, 9 will be -1, and then 0, 1, and 2. So we will receive keys in the same manner. So first time we will get a -1, which will return this one, add it to our list of lists, then 0, and etc. So in the end, we'll just return result. Let's run our code, and let's submit it. So time complexity in here, it's O of n, because like we're seeing every single node in a given tree node in a binary tree. And space complexity, we have created some here map to track it, some queue here, and in all of them, this is holding all this column number with its list of nodes, and this is holding them also tree node information. And overall, if you take a look at this, each of them has its own time complexities, space complexities in there. And that's like overall though, we are seeing all those nodes in a binary tree and then saving them in there. So overall space complexity will be O of n.